Looks like we can get started. Welcome back, everyone. So today's class is a little bit special. We're just about done with chapter 8. I think that was a pretty tough chapter. Usually applications in calculus are not easy, but chapter 8 started off nice in 8.1, not so bad 8.2, but I'd say 8.3 is a pretty tough section. As far as exam questions go, I'm probably going to steer mostly towards center of mass type problems like we see here, where it's usually just integration of these 3 steps and you're all set. The ones that have to do with hydrostatic force, hydrostatic pressure, they're good problems for homework, but I'm not going to bring those to exams because I feel like the author just didn't support those problems enough to really make it a good concept in an exam setting. So after chapter 8, we have just one last problem left to do on those notes. We're going to do even more applications of integration in chapter 9. Chapter 9 is an interesting one because in chapter 9, we're introducing differential equations. Now, if you take a differential equation class, then some of this material is just going to completely overlap. So we have to wonder, why are we doing this? The reason we're covering some differential equations is, depending on your program, you might need some already just by being in Calculus 2. Some of your classes you're enrolled in could be using differential equations already. And so this is our opportunity to practice with them a little bit. Differential equations, Math 3360 as a course, has a prerequisite of Calculus 2 and linear algebra, or Calculus 3 could serve as both of those prerequisites. So we're not trying to get too far into the subject. We're going to skip around to do section 9.1, 9.3, and 9.5. And this first assignment relative to section 9.1 was hard to really find a lot of good questions to assign, so I think this might be our shorter assignment of the year. Think of this one as kind of a freebie assignment. Still, there's some interesting math to do there, and it's us just introducing what we mean even when we say differential equations. That's our main goal in section 9.1. First, we'll do one more example in section 8.3 and then move on to the new chapter. Any questions at all, folks, before we get started? Okay, well, let's give this last problem a try. In section 8.3, the last concepts about center of mass, the process was to integrate in this following order. First, you find the area of the region here. This is a region that's going to be a plate, think something like this, uniform density. Then the x-coordinate of the centroid, or center of mass, is the reciprocal of area, integrate x times f of x. For the y-coordinate, it's reciprocal of area, integrate a half of f of x squared. They're kind of strange formulas, but I encourage you to look at the derivation for both of them. Reading is not too bad on that derivation, and it shows how this comes together. Well, any questions about those formulas there? Okay, so this is the picture when you have one curve you're dealing with, and the region is bounded by the y-axis, the equation y equals 0. We do have one problem in the homework and on the notes where that's not the situation. You might have two curves. So if the region R lies between y equals f of x and y equals g of x, here's what we must now do. First, let's draw this out just to show what it looks like. So we're going from, I'm going to try it a little bit harder on my axes. We're going from A to B. The curve y equals f of x, we think of that as being the curve that's above the g of x curve. So it might look like this when we go to plot. The second curve, y equals g of x, this one will lie below. They might intersect at a common point, say something like this for an example. They might intersect at multiple points, but the region we're really looking at is probably something that goes along like this. Let me try again. Something like this, really. So here's y equals g of x. Then we want the condition f of x is always greater than or equal to g of x. We can put vertical line segments, x equals a, x equals b. And now we have a region. Like before, we assume that this is a region of uniform mass, maybe just some weird plate that got manufactured, maybe a cast off from a 3D printer, who knows. We want to know what the center of mass is of that plate there. The first thing you have to do is calculate the area. The area is a definite integral going from A to B. And what we do is we integrate the function f of x first. If that's all you put down in your integral, it's going to give the area under this curve all the way down to the y-axis. So that's why we subtract the g of x function. It eliminates all this unnecessary area that we didn't want in the first place. So minus g of x dx. So that's how the problem is going to be set up for finding the area if we're in this land. Then for the x coordinate, we take x times f of x minus g of x, just like we see here. But I find this one to be tricky. For the y coordinate, you take a half times the function squared here minus the function squared here. But we're not saying f of x minus g of x quantity squared. We are just dealing with two terms, not three if you were to FOIL them out. So the process is highly similar. The only difference is you now have two functions that you have to contend with. The algebra can definitely get out of hand, so can the calculus. So I changed up this problem. It actually even fit with the original problem here to these curves, which would be more routine if this was an exam question. Well, any questions at all, folks, with the theorem here? Okay, putting this into effect, we have to find the region bound by the curves y equals root x, y equals x squared, and then get its centroid. Now, if this was a real exam question, you'd probably have just the graph of this. But, well, let's just do that then. Let's put down the graph of both these curves and work from there. So our top function, f of x, is square root of x. Not sure if I can change the colors of these things. Oh, well, we'll go with red on that one. The bottom function, g of x, equals x squared. And now notice there's points of intersection. So we have an intersection at 0 and an intersection at 1. We could solve these algebraically if you'd like, but if it's plainly obvious from the graph, we'll go with that information. So on both of these, we'll put down a domain, 0 less than or equal to x, less than or equal to 1. Same domain condition on this one, from 0 to 1. And finally, this is the graph that we're dealing with. Wish I could change those colors, but, well, we'll deal with the colors we got.
Press the gear.
Oh, thanks for spotting that. So gear, oh, that's kind of cool. I just wanted to match my color coding, so I appreciate that. That helps out a lot. So blue for the top, green for the bottom. Hey, now we've got decent and actual good color coding. I'll remember that trick right there. Thanks again. Seem to learn a lot of tricks from students on Desmos. In fact, the trick of finding the right domain, this curly brace stuff, that's not mine. Someone tried to teach me how to do that, to show things in class correctly. So with that graph there, this is what it would look like as an exam question. I will give the graphics, they won't be color coded. Our exams print black and white pretty much, but you'll at least have a picture. So we know from our problem, y equals root x, the top function. I'd likely label these as well, just to make sense of which curve is which. Bottom function is y equals x squared. And they do in fact intersect right at 0. The square root of 0 and 0 squared are both 0. And they intersect right at 1, since square root of 1 is 1, and 1 squared is 1 as well. I'll leave it up to the class though. This was a homework question. There's probably no graphics, and it's up to us to determine if it goes from 0 to 1. Which means we would have to solve an equation. Should we do that just for the fun of it? Okay, let's do that. So if we didn't have any graphics and this was a homework question, like say a problem in your actual homework from this section 8.3, you could use graphs to produce these. But if you want to be really sure it actually does go from 0 to actually 1, this is what you must do algebraically. We have y equals root x, y equals x squared. So we'll assume that they're equivalent and write root x equals x squared. We're finding the values for x that make y and y equal to each other from those two functions. To solve this equation, we need to eliminate the square root. So we square both sides. The square on the left is going to give you x. Square on the right is going to give you x power 4. And sorry, Bryson, I just saw that chat for the gear on the left to change the colors there. Appreciate that hint, by the way. So now this equation, subtract x from both sides. 0 is x power 4 minus x. We're getting there. And then from this equation, we want to factor out the greatest common factor, do any kind of factoring we can. 0 equals x times x cubed minus 1. That's where we would want to be. This is a equation where the right-hand side is factored, the left-hand side is 0. The only way this is true is if you plug a 0 right in here for x, or if you plug a 1 right in here for where the x cubed are, so we can read off the solutions from there. For folks really fluent in complex numbers, complex analysis, there's really 3 solutions to that, but we only take the real valued solutions since that's all we're dealing with our calculus, just real numbers. So we definitely know we're going from 0 to 1. So now we start the process of finding the centroid. And again, I'll leave it up to the class. It's always kind of fun to guess these things. Imagine that point is a centroid. I think a lot of people would say probably right around there is plausible. But would you make any changes from that? Would anyone move it left, right, up, or down? I agree with you, actually. We look at these curves, well, it's kind of bottom heavy, right? And the top over here is sharp, so it's top light. I agree with you. It's probably somewhere out here. I don't know where for certain, but it does budge where your natural guess might have been. This isn't perfect symmetry about the lines 0.5, 0.5 for x and y. But again, we'll see if we're on the right track by finding the full process. First, we need the area bounded between those two curves. So that step starts off like this. Area is a definite integral going from 0 to 1, same values that we spotted right here. You take the top curve, root x, minus the bottom curve, x squared. We've got the color coding going just fine, but just for extra emphasis, if you're thinking of the functions in this format, like in the notes above right here, think of your y equals root x as your f of x, and your y equals x squared as your g of x. So now we're just integrating this, really not so bad. That's x power 1/2 by the red dot, so it'll turn into x power 3/2 multiplied by 2/3. Then this one's a little bit easier because the exponent's exhibited. This becomes minus 1/3 x cubed. So all of that is evaluated from 0 to 1. Now, if this was a real exam question, there's parts of this that makes it a little bit faster, like the lower limit of integration being 0 helps out. All we're doing is plugging in 1. So this turns into 2/3 minus 1/3. Plugging in 0 just gives us zeros. And so finally, the total area, we already have the least common denominator. It's exactly 1/3 for the area of this region. Well, that was pretty quick. 2 more steps to go. Any questions, folks, with getting the area down? Okay, next we're just going for the centroid coordinates. That's what this orange dot is supposed to be, x bar, y bar. I think that's pretty close to the right spot, but let's keep on calculating these and see what it turns into. So here's the first coordinate, x bar. It's going to be reciprocal of area, integrate from 0 to 1. We take, let me fix that. We take x and we multiply the group of f of x minus g of x. Let's go careful with this one. Dx, and that's the x coordinate of our centroid. Good idea to copy the formula down right away, just like that, when you're learning the formula. That way you don't miss weird things like forgetting the x, the more and more you do that. But in this format, let's now plug in the actual functions. First reciprocal of area is reciprocal of 1/3, which we're integrating from 0 to 1. X is going to multiply f of x, so we might as well put that power 1/2 on that. Minus g of x, that one's x squared, dx. So the integrals are not bad, but even for this problem, it's a really long process to get every piece of this. If this was really a true exam question, I might add instructions that say, find the first coordinate of the centroid, referring to x bar, or maybe just find the second coordinate, something like that, so it's not as long of a problem. But now in this format, we need to distribute x through before we can collect an antiderivative. The reciprocal of 1/3 gives us 3. Integrate from 0 to 1. And imagine the x has power 2/2, where the red dot is. It multiplies here to give us x power 3/2. Here to here is not bad. We get minus x cubed dx. So now we're ready for an antiderivative. This is going to turn into 3 times by the red dot. It's x power at 2/2. New exponent is 5/2. Its reciprocal is 2/5 for its coefficient. This one's faster because we don't have a fractional exponent. It turns into minus 1/4 x power 4. And we integrate that whole mess from 0 to 1. Get 0 is nice. Lower limit of integration just wipes everything out. This is just altogether when we plug in a 1. 3 times the quantity of 2/5 minus a 4. Because it's an applied problem, no harm if you'd like to put this just directly into your calculator. So let's do that as our next step. We're using this as a calculator now, so let's save on a little bit of real estate. And put in 3 times 2/5 minus a 4. I get a quantity of 0.45, and notice that's what we expected to see. So good calling, folks who said to budget down and left. It looks like that's about right. And if I wanted to make it fully accurate, probably should have gone, let's see here, about right there. So that looks like it's the right location for the centroid. But let's record our results so far. This turned into 0.45. So I dropped the x coordinate to what looks like about, well, I didn't quite get there, did I? Oh, geez. 0.45 on this graph. If I look at this a little bit better, that's by 0.4. My shading marks are not helping me. Should have been more like about there. Does that look better to folks in that region? Okay, so with that, that's our centroid. And now we have to make a prediction. I mean, we don't have to, but it's always good to look before you leap on these kinds of problems. Would you expect y bar to be the same on this one? Or would you expect it to be different? I agree with you. It looks like there's actual symmetry here. The symmetry is about this line, y equals x. If that's true, then your x coordinate and y coordinates would be the same. So we're expecting a 0.45 for y bar, but if it comes out different, don't be too surprised either. Sometimes these things do kind of defy your intuition, but it looks like there is true symmetry here. So let's see if we can actually match that out. So y bar by formula is reciprocal of area, integrate from 0 to 1 of 1/2 of, and here's the formula for y bar. If it was one function, it would just be that function squared. But for two functions, we have to put in f of x squared minus g of x squared as well. Dx. So that's our formula for doing y bar, second coordinate of the centroid. Let me try to get some extra space going on here. That's not moving over the way I hoped it would. Let me just put down a border then, just so that the x bar information and the y bar information don't just glom together as one big mass of math. So now we have a little bit of separation here. This is our y bar computation. First substitution is area is a third. So 1 over 1/3 just gives us back to 3 like before. Before the integral sign, let's also move the 1/2 out of there so it's less of a distraction. So times a half, integrate from 0 to 1 of f of x is that thing, square root of x. So square that and you get just x. minus, from down here, we're squaring g of x. Looking up the function, it's x squared. So x squared gets us to x power 4 next. And now we're in business. That's not too bad of an integral to get through. We might want to go to the next page on this just to make sure we're on the right, don't cram it in. Bryson says you can grab your drawings with that lasso. Oh, let me give that a try. Thanks for mentioning that. Hey, then now that we've got it, Control X. Hey, that works out really well. Thanks again for that assistant bit there, Bryson. That way you're not trying to cram all the things in one page. That works out a little bit better. Let's just say that this continues. Microsoft is really finicky with digital ink, by the way. So if you're using Microsoft Word, it takes a lot of work sometimes to make it work out, but that lasso trick actually helps quite a lot. So final things to do. That turns into 3/2. Antiderivative of x is a half x squared. Of x power 4, its antiderivative is a fifth x power 5. This is going from 0 to 1. So like before, pretty fast on this stage. It's 3/2 times 1/2 minus 1/5. Throwing all that in the calculator. And also looking at what we got before. Notice it's not exactly the same, but if this works out algebraically, working out the fractions, then our prediction is correct. So 3/2, 1/2 minus 1/5. Somehow, some way, if you do the fraction arithmetic really carefully, this really comes out as a 0.45. So even though you don't have to put this on your work, it's not a bad idea to give one big overall conclusion. We can now say, therefore, x bar, y bar are both exactly 0.45, 0.45. So that's going to be the centroid for this weird plate right here. Well, any last questions, folks, on getting through this one? Okay, there's exactly one like this on the homework. So if it makes it to the exam, then it might be kind of unusual. Great exam questions are the ones where we do more routinely, like say, this version. We did several of these. There's several more in the homework. So I'm thinking this would be the more likely exam question that you could expect from section 8.3. But this one, think of it as just extending a little bit further using the same tools. You can also calculate the centroid if your region is bounded between two actual curves like this. But this is the point where the notes finally end in section 8.3. Congratulations, folks. I think these are the trickiest notes to get through in all Calculus 2, thanks to that first part of section 8.3. But now that we're done, we're moving over to chapter 9, working on differential equations. Any last questions or comments whatsoever before we change to the next section? Okay, let me just get this. It's like my second time saving it, but just to be sure, let me get that saved up. You know, Microsoft's struggling when you get artifacts like that from just trying to close something. This is like the limit of what it can do reasonably, I think. Now we're going over to chapter 9. Okay, so chapter 9 is a pretty weird section for us because once again, the actual course on differential equations at our university, Math 3360, requires Calculus 2 and linear algebra as their basic prerequisites, or Calculus 3. So all we're doing is we're chipping away at the subject, giving just some extra ideas of what differential equations really are to help out when you go into the actual differential equations course. It starts off really, really abstract. An nth order differential equation is a function, so uppercase F, that combines an nth order derivative with the n minus 1th order derivative all the way to the second order derivative, the first order derivative, the function, and the variable into some equation set to 0. So that's kind of nasty in a way, but that's the base definition. Nth order just comes from the fact that there's an nth order derivative somewhere when you put all this together. And it might be that most of these things are all zero, and there's just a couple things that actually survive, the highest order of that derivative. So for an example of a second order derivative, or it looks like this one is first order derivative, it'd be something like this. So we have first order derivative right here, a function of x, variable x times another function y, and another function of x, all set equal to 0. So that's what we mean by a differential equation. Not too sure what the solution would be of this is just a random equation. But any questions at the moment with the idea of what a differential equation could even look like? Okay, differential equations are one of those things where you've really been studying it for a long time when you're in an algebra class or a calculus 1 class, but now we're just trying to make formal what we're trying to say when we write differential equation. It's an equation like this where the unknown is not necessarily a number, it is a function y equals f of x. So that's kind of a big leap all of a sudden. We're used to equations like, say, 3x plus 5 equals 0, for an example, where the unknown is just a number. But here, the unknown is a function that satisfies all of that information simultaneously. So, like I said, we've been dealing with differential equations a lot in math classes, and that's what example 1 is all about. So it starts by saying, let P of t denote a population size at time t. So maybe this is say, the population of Pocatello or Idaho Falls, something along those lines. If you write down this, that's a first order derivative. That's the rate of change of the population. Assuming the population's growing, this would have a population sign, and so it represents the population's growth rate now. Here's where it gets interesting. This is a problem that we've seen a lot in algebra and in calculus. Suppose it is a reasonable assumption to assume that the given population grows at a rate that is proportional to the size of the population. Well, that's a lot being said just in this one sentence. So let's break it down. It says, assume the given population, that's referring to P of t, grows at a rate, that's referring to the derivative. So let's take this, dp dt equals, and that just came from here saying that the population grows at a rate. The moment they said rate, they're talking about that derivative right here. They say that is, well, from there we could just say is, so let's just put extra equalities for that portion there, proportional to the size of the population. That means the right-hand side is just going to be some constant. We'll use k for the proportionality constant, multiplying this part, the size of the population. That's P of t from right here. And so that's the differential equation that results from this information. And this information is not always reasonable. The population size of Idaho Falls would not grow exponentially year after year, century after century, but it is reasonable over short time frames. So if it's an experiment with bacteria, this is probably a reasonable assumption for about 30 minutes until resources run out and the population begins to collapse instead of grow. So we wrote down a differential equation that models population growth. Some of you might already know the solution to this differential equation because it's so common, but that's what we mean by modeling with differential equations. We take information like this, try to convey it as a derivative relating the function. Now the unknown to this equation is a function once again. We want to know what function p satisfies that differential equation that came from this information above. But any questions, folks, on part A, where we just write down the differential equation? Okay, now that we have it, we also want to solve this thing. And how we're going to solve this? Well, as the section indicates, if you're talking about differential equations, there has got to be a differential somewhere. So that's our idea with this equation over here. We're not going to be solving a lot on these notes, but we will be solving them in section 9.3, 9.5. So think of this as mostly a preview. This part's not part of the homework exercises, but this is how it would go down if we really want to solve this equation. As it stands, dp dt, that's a derivative. But if we view it as a differential, we could write it out this way. dp equals k times p of t dt. So in this land over here, this is a derivative. It's not a true fraction in any sense of the word. What this thing is dp dt is just a way to say lim as h goes to 0 of p of t plus h minus p of t divided by h. So that's what this Leibniz notation for the derivative is indicating. It's just the limit as h goes to 0 of the difference quotient. But in the land of differential equations, we do regard this as not the actual derivative, it's the differential. dp is one variable, dt is another variable, and we could just simply take this, multiply to the right-hand side so it lands here. Now we're not thinking of dp and dt as a derivative at all. We're looking at differentials, like we did on the first day of class. Differentials just keep on coming back. So that's a pretty bizarre step with the clarification here, just to kind of cover our trail and how we got here. Any questions to that stage by the red dot? Okay, once we do something like this, view this as a differential with an equation or differential equation, we want to start organizing what goes where. So we're going to put in, instead of p of t, we typically view it this way. dp equals k times p dt. So instead of writing out p of t, we're using more of this notation. P is just going to represent the whole function without the function notation p of t. It makes the next step a little bit more clear. We want p to go to the left-hand side together with dp. So divide p on both sides. We get 1 over p. dp equals k dt. But because we took that step, we have to assume p is not equal to 0, just for this side of the algebra. However, p equals 0 does solve that differential equation. For example, if p equals 0, then the left-hand side, dp dt, sorry, seem to have clicked on something there. There we go. dp dt is 0. Because if the function is 0, the derivative of the function, that's the derivative of a constant, is still 0. And the right-hand side would be k times 0, which is equal to 0. So p equals 0 is a solution. But it's like the most boring solution because remember, p is the size of the population. If I'm saying p equals 0, that means the population of Idaho Falls has been wiped out. There's no survivors. So we're not so interested in the growth rate anymore. It's clearly just 0. No survivors means no growth rate. So that's just a weird side solution to the original differential equation. I needed to discuss it because once we divide, we're assuming p is not 0. So we have to ask, is p equals 0 an actual solution? It really is. That's kind of remarkable in a way, but maybe not super useful again. The spirit of these problems is that you have a positive population size. Nonetheless, we're in a weird spot here. We have a constant times dt on the right. The reciprocal of p times dp, oh, that's on the left. But one thing you can do to an equation is integrate both sides. And notice on the left-hand side, we're integrating p with respect to p. The right-hand side, we're integrating a constant with respect to t. That's something we can absolutely do. This is really truly just an application of integration still. Let me get some extra space down here. First, we want the antiderivative of 1 over p. Think of that as a 1 over x. You would get the natural logarithm of the absolute value of p from that portion. There is a plus c for the constant, but when you're solving two integrals, one on one side of the equality, the other on the other side, we aggregate our constant to just one side. So here, the integration would end, and we'll just go equals. This one's kind of tricky, but visualize that one as antiderivative of 5 dt. If k is 5, the answer would be 5t plus a constant. If our constant is a little bit more vague, just a proportionality constant k, same idea. We'll take k times t plus a constant. So that's after integrating the differential equation on the prior line. Now we're solving for p, and we can do this at this stage. We just need some tricks with the exponential functions, some tricks with absolute values, and then we'll finally get there. Any questions, folks, to that stage? Okay, next stage is we have a logarithmic equation. We're converting into an exponential one. The way I personally like to visualize it is I take the left-hand side and think of it as an exponent now. It's an exponent to base e. So e to the power of the natural logarithm of absolute value of p, I have to do that to the other side, is equal to e to the power k times c plus a constant. The reason we took that step is we get a great cancellation going this way. So p is no longer locked up in two functions. It's outside the natural log, but still inside the absolute value function. So on the next step, absolute value of p rather, is this stuff. We can use properties of exponents to simplify this even. This could be written as e to the power of c times e to the power of kt. The reason that works is a base times a base just causes us to add up the exponents, getting us to that last step. Finally, if we want to eliminate the absolute value right here, there's a really fast trick on that. It produces two different equations, one with a positive sign and one with a negative sign. And it's very common to abuse the notation and just write it this way as one equation. P is either equal to positive or negative e to the power of c times e to the power kt. So that's our solution. It just looks awful. But in differential equations, this is what we often do with our constants. We'll say, let c1 equal positive, negative e to the power of c. So on the next line, we can say p equals c1 e to the power of kt. We're almost there. That's just about the solution, but we can go even further than this. First, any questions, folks, by the red dot? Okay, so e to the power of c is kind of concerning if we only had that as a constant. The reason that's concerning is if we write out something like y equals e to the power of x, then no matter what your value is for c, right here where it's highlighted in yellow, it's always positive no matter what. But it has to be positive or negative. So we took this step, positive or negative for our constant, and called it just c1. But you know what? That causes a different kind of problem. Y would be equal to negative e to the x. Think of the x as the value c, where it's highlighted in yellow. So now we have all of the negative numbers, we have all the positive numbers, but there is still one number you will never ever hit on this graph, and that's 0. We can move far to the left, zoom in, and you'll observe these curves just get closer and closer to the x-axis. They will never hit them from either side. Why is that a problem? Well, if we let c1 be our answer, where it's positive or negative e to the power of c, we're saying that that constant can be any positive number, any negative number, but that it cannot be 0. And that's a lie in this problem, because 0 is a solution. So we come down here and we convey on our last step by saying, therefore, P of t equals c, so we're back to a general constant, e to the kt solves the differential equation where C is any real number. So it started off weird when we went through the development. We had only positive numbers, e power c. When we went to C1, we had all the positive and all the negative numbers. But the moment we observed that that's a true solution, we bring back a zero and we just say any real number down here once again. So that's our claimed solution to our original differential equation. So that solves this one up above here. In college algebra, they usually just give you that equation and you work with it. In Calculus 1, this enters the picture and we see how that problem gets tied in with other results. But now in Calculus 2, we're more interested in the process of finding the solution and then verifying it really is a solution by feeding it back into the differential equation and testing it. First, any questions at all, folks, on producing the solution? Okay, so what we're going to do next is, going back to our original analogy, the equation here that we're solving, or the equation down here we're solving, the unknown is a function. And even if we were back in the land of, say, 3x plus 5 equals 10, we would claim a solution is, let's see, 2/3, or let me try, subtract 5, divide by 3. We would say 5/3 is a solution, but the way we check that is we take the supposed answer and feed it back and see if we actually balance and get equality right here. For differential equations, the analogy is not too different. That's the original equation. That's the solution. So we need to take that, plug it back up inside here to see if it really was a solution. So that'll be our next step, part B. Well, how should it start? Maybe by copying down the differential equation. So dp dt equals k p of t. So that's our original equation that we started with. Next, to verify the solution, part B solves it. We grab that function right there, the solution part B, and we start with just differentiating it. Take dp dt. So this is the step where we're probably pretty sure we have the right answer, unless we suspect there might have been some weird algebra or mistake above. So we're feeding the function, that right here in yellow, let's just highlight it, into the original differential equation. So I'm starting off with the left-hand side, dp dt. So differentiate the function in yellow. We're over here. First thing we do is the constant multiple rule. C is unaffected. We're really differentiating with respect to t, e to the power kt. So that's my first step. This is a tricky derivative because of the weird constants everywhere inside here. So we're going in stages. That's the constant multiple rule. Next up is the chain rule. We'll have the constant c multiplied by the derivative of e to the power kt, which is itself. In parentheses, just to emphasize, that's the inner function in the chain rule. And we multiply by the derivative with respect to t of kt. Back over here, that derivative is just k. Imagine, visualize differentiating 5 times x or something like that. The derivative is 5. So this turns into, first from here, we're just copying c e to the kt times, this derivative is just a k. And now when we look at this, c e to the kt, that's just the p of t function originally. So on our next line, we can say that this equals the constant of proportionality k. For this part, you can write p of t or just p, it's up to you. Let's go with p of t. And that means we've balanced the equation. We started on the left-hand side by differentiating, and then through some algebra, chain rule rearranging, and substitution, we were able to put p of t right there. it matches the right-hand side now. And so we can now say, this shows P of t equals C, either the KT, is a solution. So we did it, folks. That's the process of finding the solution. We're going to delve into that a lot more in sections 9.3, 9.5. But what we're mostly doing in section 9.1 is seeing how differential equations get built and testing if we have an actual solution to the differential equation by taking these steps here in part C. Any questions at all, folks, on this adventure so far? Okay, so my first example is more just saying what differential equations is all about, how to model something and how to solve one. Starting in example 2, these are where the problems are very, very highly similar to what's going on in the homework in this section. Again, I couldn't really assign a lot. So 7, 8, 9, 11, and 12, these are all just giving you differential equations. They'll give you that something that is or is not a solution and where you need to verify it. I did say for full credit on those problems, you do need to show all the algebraic and calculus steps on verifying. But the major thing that's easy to miss is you also have to make an assessment, an overall conclusion at the end by saying either yes, y is a solution, or it's not a solution. Much like with what we did right here. Don't forget the conclusion of stating whether you have a solution or not. So here's our next batch of problems. Determine whether the given function, that's the given function right here, y equals sine x minus cosine x, is a solution to the differential equation. These equations look differently all of a sudden, but just keep in mind, that's just a matter of notation. Y prime is dy dx. Oftentimes, if we're just writing down an equation as fast as possible, we like Newton's prime notation. But we'll also find oftentimes if we're going to solve the differential equation, Leibniz notation is most often really necessary, especially with the method we did to solve our equation for the day. So now, here's the whole setup. That's the differential equation. And this is a great way to start it. Take one side. Usually it's going to be the left-hand side where it's more complicated. Y prime plus y, and just start calculating things. If this is your y, then we do have a y prime. Let's calculate right down below so we can plug it in down here. Y prime is the derivative of sine, which is cosine, plus the derivative of negative cosine. With all the negative signs, that turns into positive cosine, positive sine. So that's what's going inside here for y prime. For y, that's just the original function since it has no derivative sign on it. Now this is just a method of putting down substitutions. So let's start off with y prime. It's cosine x plus sine x. Then move over to plus, and now the next substitution for the function y, we're just dropping in exactly what they provided. Sine x minus cosine x. We often have to do a bit of algebra with these things. So the algebra in this one is just combined like terms. Cosine functions cancel, and we have 2 copies of sine x. So it's equal to 2 sine x. There's nothing further I can do with that. So this is the stage we make a comparison. Is 2 sine x equal to the right-hand side? It is. We're in business. We just showed that y prime plus y, through the use of equalities, connects to sine x. That means the original differential equation is valid for that function, y equals sine x minus cosine x. That's one solution, but there's infinitely many more, potentially. So we'll just say here, our little shorthand for therefore, y is a solution. That's kind of unsatisfactory in a certain sense because when you're solving ordinary equations, say 3x plus 1 equals 0, you would say x equals negative 1/3 is the solution. And that's very satisfying because you get to use the definite article to say that's the only way to make the equation true, and there's no other way to do it. Over here, we don't get to say that. We use the indefinite article and we say we found a solution, and there's likely a whole bunch more, unfortunately. So differential equations doesn't obey the same things that you would expect. One equation will have infinitely many solutions. But any questions at all, folks, on the process of verifying a solution? Okay, really it's kind of like verifying you have a trigonometric identity, starting with the left-hand side, working things out till it matches the right-hand side. And really all it's about is take your derivatives, do some substitutions, and see if you can balance that differential equation. So here's our new equation to work out. If it's a square root function, then the derivative is not too bad. With the square root, it always goes this way. 1 over 2 times the root of whatever you've got. It's also a chain rule when you differentiate this, so we'll also take times d by dx of the input as well. So what goes inside the root is the inner function, 1 minus x squared, which means through the chain rule, you're differentiating by that same inner function, 1 minus x squared. So that's our first step to differentiate. Denominator is done on this one. 2 root 1 minus x squared. And we'll take into the numerator this thing multiplied inside. And this turns into just a negative 2x. So that cancels up and we get negative x divided by root 1 minus x squared. It's a good idea to simplify it as much as possible, just makes all the other work much more streamlined. So now with that done, first thing we do is take the more complicated side of the differential equation, definitely the left-hand side on this one. It's y times y prime minus x equals 0. We know what y prime is, we just calculated it. We know what y is, that's the supplied function coming from right here. And I did take a little bit too much, my mistake here. When you're copying these things down, you usually just want to copy one side, not the whole entire equation. So let me write out this way. Next, what I want to do is start making the substitutions, write out a huge trail of equalities, and hopefully end up at a 0 here, the right-hand side. So first step, plug in y, that's root 1 minus x squared. Multiply it by y prime, that's this thing, negative x over root 1 minus x squared. The rest of it is just minus x, so go minus x like that. And let's see here. I think we've got it, folks. We just need to do some cancellations. Square roots are eliminated, and we get altogether negative x minus x, or a negative 2x altogether. Comparing this, we make this comparison, take what we produce from the left-hand side, compare it against that right-hand side, and notice it's not equal to 0. So if we can balance the equation by putting in y times y prime minus x, we got negative 2x. Looks like it should have been positive x to really hit 0. We just put not equals, and we convey our solution by saying, therefore, y is not a solution. Not to this differential equation. I'm sure it has solutions, but that's not one of them. Any questions at all, folks, with the solutions here? Okay, so that's the whole process of verifying if you have a solution or not to your differential equation. But the sad thing about these equations is that they're not very exciting. I have no idea what real-world phenomenon these could satisfy. Actual honest differential equations are a little bit more messy, like this one right here, modeling either population growth or decay. These are kind of messy equations to work with. And here's another one from the notes. Felt like this isn't enough for us, so here's a third version of doing the same process. But this one's a real application from physics, and it's something that you can observe in real life all the time. Imagine two poles, power line cables, hanging from each of the poles. The actual curve that your cable makes as it sags due to gravity is called a catenary curve. That curve right here, y equals f of x, is the curve that shows the cable hung between two poles, satisfies that differential equation. And it's kind of a crazy one because it's a second order differential equation coming from that right there, second derivative of y. So this one is a second order differential equation. So it's equal to that on the left, the second derivative. We have some arbitrary constants. Rho is usually density. We can carry that over from section 8.3, but here it is linear density of the cable. G is probably what you're expecting, the acceleration due to gravity. And T is a new variable. T is something that you would have to measure, verify experimentally. It's the tension of the cable at its lowest point. So there's got to be ways to measure that kind of thing. You'd have to ask the physicists. Probably that's something they probably really do in a lab. Here's where it gets a little vague. The author says, and the coordinate system is chosen appropriately. I have no idea what he means by that, but probably what he means is there's a little bit more physics that goes in the background of this than what meets the eye. So you have to have the right coordinate system for all this to work out, but that's your differential equation. We're being told to verify that the function that y equals t divided by rho g, hyperbolic cosine of rho g x divided by t, is a solution to the second order differential equation. So hyperbolics are the solution to this thing, which again is always a great surprise. And this is like the application for hyperbolic functions. They describe the curve when a cable is hung between two poles highly accurately. No other function as great as a candidate as this one. But we've got to show it satisfies this differential equation right here. So we'll start off by doing, how about that part? We're going to begin with the left-hand side. That's our equation there. We have to calculate the second order derivative. So we'll do it right away. So here's the first order derivative, dy dx. The whole function looks like this. First, it's the constant multiple rule. T divided by rho times g is unaffected. We take the derivative of hyperbolic cosine, and it turns into hyperbolic sine, but positive. If you feel a little rusty about these, then take a look at this document right here for hyperbolic functions. It gives you the setup for what it's all about. You're solving equations on a hyperbola to define the functions. If you scroll down enough, this is where your derivatives and potentially helpful identities are on this set of notes as well. Notice this looks almost exactly like the trig table, except a negative that would have been here is on the right-hand side. So that's the major change with signs for these functions. So back to this problem. The derivative of hyperbolic cosine is positive hyperbolic sine. So sine h rho g divided by t times x. But this is also a chain rule problem. You have to multiply it by the derivative of the inner function. That's just a constant times x. So like in the last problem, we'll just be multiplying by rho g over t, since the derivative of x is a 1. So all I've done on that last product was differentiate this, and it turns into that. Which means we get some cancellations. This t divided by rho g will cancel with its reciprocal on the far right. So the first order derivative is hyperbolic sine of rho times g divided by t for tension times x. So that's one derivative down. I don't know how that turned black. That's weird. We're going up to the second order derivative, so we'll just do it all over again. So starting from here, d2y dx2, that's our second order derivative, is first the derivative of hyperbolic sine. Let's put in a little bit of space there and write it as sine h rho. Oh, hang on, I forgot to differentiate it. Let me try all over again. The derivative of hyperbolic sine is now back to hyperbolic cosine, still positive. So cosh rho g divided by t times x. They come over here. By the chain rule, we differentiate that function. The derivative of all this is just rho g times t. I'll put it out in front of the function. Just for convenience, no other reason. So we did it, folks. That's our whole left-hand side. Next thing we're going to do is focus on this right-hand side and see if we really get that thing right there, that second order derivative we just calculated. Any questions so far, folks, with the approach? Okay, just to organize, let's call this left-hand side, that whole bit there, and now here is the right-hand side. It starts with a bunch of constants, rho g divided by t, multiplying a square root of a 1 plus, and notice we already did the derivative here. That's the first order derivative, because the power 2's purpose is just to square the function. Also, just for a cool connection, that's a portion that you use to find the length of the curve. So it seems likely that that'd be in the derivation, because we would want to know the length of the cable that's hanging between the two poles. So that seems to be a likely artifact from the length of that curve. Now, taking this portion right here, raising it to power 2, just means we are taking that first order derivative, hyperbolic sine h, of rho g divided by t x, all to power 2. Went a little bit crazy with my space there. 2 parentheses, and that's finally the right-hand side. All I've done is inputted this first order derivative that's simplified to here. Now, continuing on the problem, well, we can write that this is hyperbolic sine h squared. That's not a huge step, but we would get 1 plus sine h squared of rho g t times x. And I noticed I forgot to copy something in. Let me see if I can sneak it in there. I forgot the constant out in front, rho g over t. So far, so good, I guess. We're trying to land at cosh, rho g divided by tx, and we have all this mess with the square root. At this stage, if we were in section 8.1, 8.2, we'd be reaching for trigonometric identities. But there's a good trigonometric identity for this one. Recall from the Calculus 1 notes over here that if you're dealing with trigonometry, you define your functions this way. This is the reason that cosine squared plus sine squared is equal to 1. It comes from that equation. With hyperbolics, there's a minus. Hyperbolic cosine minus hyperbolic sine, both squared, is equal to 1. We take that equation and drop it inside here. We can say cosh squared of x minus sinh squared of x is 1. Add hyperbolic sine to both sides, and we get cosh squared of x equals 1 plus sinh squared at x. You can't do that with ordinary trigonometric identities, but you can with hyperbolics because the core identity has a negative sign right in the middle. So 1 plus hyperbolic sine squared is just hyperbolic cosine squared. So the next step, we've got rho g divided by t root cosh squared rho g divided by t times x. Next problem we have is we're constrained by algebra that says with definitiveness that the square root of x squared is the absolute value of x. The power 2 doesn't just cancel out. We need to know more about the function. So let's take an extra step here and call this rho g divided by t, absolute value of cosh rho g divided by t x. So we're almost there, folks, but this function, d2y dx2, that left-hand side, did not have absolute values on, so we need a way to pull it off. The way we get absolute values off this thing is we just look at the definition of hyperbolic cosine one more time. So here's the notes once again. Let me see if I can shrink that down just a little bit. So hyperbolic cosine is the second coordinate of this right half of a hyperbola. This is why we call them hyperbolics. It gives the area to come out just right here, but you can also just plot hyperbolic cosine. If you did that, here's hyperbolic sine. That would be really bad. If there's absolute values around hyperbolic sine, you can't just drop them because hyperbolic sine is either negative or positive. But hyperbolic cosine is this curve right here. It is always positive no matter what. And so we get to drop absolute values immediately just by knowing the geometry of that hyperbolic function. And it does seem plausible because for this function, it's the second coordinate that makes that area come out true. But this point can also move out to this region. This is why hyperbolic sine could also be negative, but hyperbolic cosine is always positive. This point is constrained to this right-hand side of the curve, which makes that work out. So that's a lot of talking, and the punchline is we get to drop absolute values. This turns into rho g over t cosh rho g over t x. So what have we done? We have shown that the right-hand side equals this function, and so does the left-hand side. Same exact function each time. Let's convey that with just a little bit of highlighting because we worked hard on this, so let's hit it with that. We still need a conclusion though, so watch out on real homework questions. You could lose a point just by not giving the overall conclusion. The overall conclusion is, therefore, y equals t divided by rho g cosh rho g divided by tx is a solution. But one of many. That's another weird thing about these things. Well, any last questions, folks, on verifying if we have a solution in an actual applied setting? Lots of differentiation, and this one was a big throwback, just looking at hyperbolics one more time, since they have a way of coming up here and there. We're not done with these notes, so when we come back on Wednesday's class, we'll do one more applied problem here to match the last homework exercise in the homework set. But this looks like a great stopping point for us, folks. Sorry for running over by about a minute. We'll return the time balance by ending a little bit early next time, I'm sure. Any last questions at all then before we call it the day officially? Okay, well, have a great night, everyone. When we come back, we'll finish off these notes and start off section 9.3. All 9.3 into is looking at that in more detail, how we solve that equation. We're going to make that formal and official in 9.3. But have a great night, folks. I'll see you all on Wednesday.
Thank you.
You bet. And to get your question there, thanks. The rho and G and T flip. Let me see. So from here, oh, I think I see what you mean, Bryson. It was really because of, in this derivative right here, you have the T rho G that started out. But then you differentiate to get hyperbolic sine, and the chain rule gave us rho G T again. So they just fully canceled out on this step. But then on the second derivative, when we differentiate this again, we get rho G and T, which is the reciprocal of that T divided by rho G. So it was just an artifact of differentiating twice and then using the chain rule twice. Does that make sense on where that came from, Bryson? Awesome, gotcha.